Hello, my dear students, and welcome to chapter number 5 under the title Bipolar Junction Transistors. Actually, this is one chapter toward the termination of this course. In the previous chapter, we have tackled together what's called the metal oxide semiconductor field effect transistor, or what's abbreviated by MOSFET. Now, we will turn to the second most famous transistor ever, which is the bipolar junction. Bipolar junction transistors are historically uh, invented before the MOSFETs. However, due to the implementation of the MOSFETs in electronics and especially in the digital electronics sector, that promotes MOSFET to be the most useful and the most famous type of transistor. However, the BJT or the bipolar junction transistor still have some market share, especially when you are going to high power or what we call it the power electronics application. In this application, bipolar junction transistor play a very important role. Now, let's share my presentation slide and start together chapter number 5 under the title of bipolar junction transistor. Perfect. So I think you can now see my presentation slides, and also let's also open our camera. Sorry, not our camera. Let's open our laser pointer. That's perfect. Okay, now everything is working fine, and let's now start together this journey dealing with the bipolar junction. As we did for the most, let's start with the two-dimensional and the three-dimensional schematic for a bipolar junction transistor, as well what's called the BJT. It's actually somehow similar to what we did for the MOSFET. If you remember, in MOSFET, we have two types of MOSFETs. We have what's called the N-channel MOSFET, and we have what we call the P-channel MOSFET. Similarly, here we have two configurations for a BJT. We have what's called the NPN junction, as you can see here, where we have a N substrate, then we have a B well, then we have an N well. So if you are crossing this junction in this manner, you will find this NPN junction. And this is abbreviated as a circuit model in this famous transistor schematic. I believe you already see this hundreds of times before in your electronics courses. So this is the what we call the NBN transistor, and the other alternative, which is the PNP transistor. Similarly, we start with the P substrate, then we have an N doped well, and then we have a P doped well inside the N well. So we have P and P well, as you can see, and this also, as you can see, the schematic, you can differentiate between these two schematics using the direction of the arrow. So in the emitter case, where when it's an NPN, the current is going toward the emitter. However, herein the current is going from the emitter. So the current here is ingoing, so it is outgoing from the emitter, and the current here is outgoing from the emitter. Okay, so this is the configuration. Again, we are doing the same procedure we have already implemented for the PN junctions, for the die in chapter number 3, and for the MOSFET in chapter number 4, or chapter number 5. So, so I'm sorry, PN junction in chapter number 2, and MOSFET in chapter number 4. I'm sorry. So we will start first, as usual, with what's called the energy band diagram. Here we have, if we consider, for example, this one, which is the NPN junction, if we consider this as the MOSFET or as the BJT under study, then we are going to study this PN or NPN junction, energy banding. And this is actually a very easy energy band diagram. You can find it here. Again, this is under thermodynamic equilibrium. We know that this is under thermodynamic equilibrium because simply the Fermi level is horizontally aligned. This is the N region. It's an N region because the Fermi level is more toward the conduction band. Another N region here, and this is a P region where the Fermi level is more toward the valency band. So if you have a very good memory, you will recognize that we already see a similar energy band diagram during our MOSFET lecture, because when you make a cross-sectional source channel drain in an N-channel MOSFET, you will find it NBN because you have a source which is N, a drain which is N, and in between the channel region and the thermodynamic equilibrium is a P, so it's NPN junction. So we have seen a similar or maybe a typical energy band diagram in the MOSFET. So now, as we usually do, we check the carrier transport capabilities for the majority carrier. So here we have a majority of electrons in this region, in the left-hand right region. And here also we have a majority of electrons in the right-hand region. However, these majority carriers are not able to move simply because of this barrier, as you can see. Here we have a barrier, and here we have a barrier. So electrons are not going to move from left to right or from right to left because there is a barrier. Similarly for holes, here holes will not be able to move because this is a barrier with respect to holes. Please don't forget that hole energy increased by going downward. So the holes here, which is a majority carrier, are restricted of movement due to these two barriers. Or actually, in order to make life easy, you can easily consider this as a 2p-n junction. So what I can make in a very easy manner, if I use the here, yes, this one. If I make this separator, so as you can see, you can easily consider this NBN junction as two connected p-n junction. In the left-hand side, we have an NB junction, and on the right-hand side, we have an NP junction. And both, of course, under thermodynamic equilibrium, accordingly, no current will move. We know that in a p-n junction, whenever the diode is under thermodynamic equilibrium, the output current is equal to 0, which is the origin point in the IV curve for a diode. So this is simply like that. Now, as usual, our target is to push the majority carriers to move. We have two types of, or not two types, we have two connected p-n junctions. So what is the combination we should make in order to make the majority current move? What do you mean by combination, my dear student? A combination means that what biasing condition? It's very simple. We have two p-n junctions. For each p-n junction, we have two biasing conditions. We have either a forward bias, whenever you connect the N to a negative and the P to a positive terminal of a battery, or we have what's called the reverse bias, whenever you connect an N to a positive and the P to the negative. So, as you have two diodes, two p-n junctions, and each of them have two conditions of operation, then we have an overall of 4 conditions of operation. Either to make this forward, the first one forward, and the second is reverse, or the first is forward and the second is forward, or the first is reverse and the second is reverse, or the first is reverse and the second is forward. 4 combinations, very simple. So here we have what's called the emitter, the base, and the collector. Accordingly, we have 2 junctions. We have the emitter base junction, and we have the base collector junction. So this one is the base collector junction, and this one is the base emitter or the emitter base junction. What we are doing now is we are going to investigate the effect or the impact of these 4 different configurations by connecting these 2 junctions into either a forward bias or a reverse bias. And then we can check the impact on this. Okay, perfect. So let's start with the first combination, which will turn to be the most interesting combination. Okay, so let's do it. Okay, so let's start with the first combination. I will start with adding a voltage between the collector and the base. And I will put this forward I will put this voltage in a biasing condition to make this base collector junction in a reverse bias. So I will make this N collector connected to a positive terminal of a battery, and the base collector is connected to the negative terminal of the battery. So this base collector junction turned it to be a reverse bias. This is the case, as you can see. Now, as you can see here, the positive terminal, which is this red circle, is connected to the collector, and the negative terminal, which is this blue one, is connected to the base. So this junction is a reverse. And following our understanding to the operation of a p-n junction, whenever you connect the collector and the base to a reverse bias, or whenever you connect a p-n junction generally to a reverse bias, what is going to happen that you will have a wider depletion width W, a higher potential V naught plus VR. So simply what will happen that this barrier is going to increase, which is something like that. Now this is a barrier with a larger height with respect to the thermodynamic equilibrium case, because simply you add reverse bias. Herein, you will find that nothing has been changed, because under thermodynamic equilibrium, electrons from the emitter are not able to move to the right because there is a barrier. Similarly, electrons in the collectors are not able to move to the left due to a barrier. Now, what you did is simply that you increase this barrier. So, at this condition, still the majority carriers here or there will not be able to move. Accordingly, you don't have current. Similarly, of course, for holes are still restricted, here with a very large barrier, and here with still the thermodynamic equilibrium. But please don't forget that we still have another junction. We already connected one junction, which is the base collector junction. However, the other junction, which is the emitter base junction, is still free. So what we are going to do now, my dear students, is that we are going to turn this base emitter junction to be a forward bias. This can happen when you connect a negative voltage to the emitter and a positive voltage to the base. So in this case, this p-n junction will turn it to be a forward bias junction. Then let's see what will happen. So this is the case. Now, negative potential is connected to the emitter with respect to a positive potential connected to the base. So the base emitter junction turned it to be a forward bias. Accordingly, when a base emitter junction or whenever a p-n junction is turned to be a forward bias, that simply means that you will no longer have a barrier and electrons will freely move from the n side to the p side, and holes will freely move from the p side to the n side, which is the case here. So let's now study the life cycle of an electron and holes, by the way. But before doing that, let's check again. What we did now is that we connect the base collector junction to be a reverse and the base emitter junction to be a forward. So electrons will freely move from the emitter to the base. This is simply because no barrier exists, as you can see here, because by adding a forward bias, you get rid out of this barrier. So electrons will move freely from the emitter to the base. Then electrons reaching the base will find a very huge drift here due to the reverse bias between the base and the collector. So electrons will going to drift very quickly to go to the collector. Accordingly, you can see that electrons move or complete journey from the emitter, passing to the base, reaching the collector. And accordingly, you will start to have current. This current, as you can see, my dear students, is a current due to electrons. However, generally, you can also have current due to holes. This is simply because this is a p-type region. So you have a majority of holes here, as you can see, this white circle. Whenever you conduct this base emitter junction to be a forward bias, then this barrier also will be disappeared. And then holes now can move from the base to the emitter. And please don't forget that you already also have some holes here which is a minority carrier that can drift from the collector to the base and then from the base to the emitter. But of course, this is a minority carrier current, so it's somehow low weight with respect to other components. That's why, my dear students, we call this a bipolar junction transistor. If you remember, we have studied before the word unipolar and bipolar 2 times before in this course. In our metal semiconductor lecture, whenever we compare the p-n junction with the Shockley barrier die, and in the MOSFET, where we studied that the MOSFET are a unipolar device because the current in the MOSFET is only due to one type of carrier, either an electron current whenever it's an n-channel MOSFET, or a Hall's current whenever it's a p-channel MOSFET. So this is the configuration for the NPN junction and how the NPN junction operates, where the majority of the current is due to electrons and some of the current is due to holes going from the base to the image. Okay, we are going to illustrate this in more detail whenever we will start the EP model, but let's now study a very important drawback in the operation of a BJT. Before we do this, we have to define this as what we call the active mode in a BJT. So the active mode in a BJT is the mode at which the emitter base junction is a forward bias and the base collector junction is a reverse bias. This is what we call the active mode in the BJT, which is the most famous operating mode. As I discussed earlier, we have 4 operating modes for this BJT. The most famous one is the active. But as I mentioned, we have a problem here. We have a drawback here. What is the drawback? That's the journey of the electrons starts from the emitters. Then electron, due to this forward bias, starts to move from the emitter to the base, and then there is a huge drift where electron starts to drift from the base to the collector. But during this journey, electrons pass through the base. And as you know, the base is a p-type region. That means that there is a huge amount of holes is located in the base. Once we have electron, which is a negative charge, passing in a place where there is a huge amount of holes, which is a positive charge, then the probability of what's called the recombination starts to appear. A recombination, if you remember, we have already covered this in our revision lecture in chapter number 1. A recombination is a process where electrons lose energy and return back to the valency band to recombine with the hole. Here you have a huge amount of electrons, a huge amount of holes, then basically you have a high probability of recombination current. That's why recombination current is one of the very important parameters associated to the BJT. And of course, as I mentioned, it's a negative point, or it's a disadvantage from a BJT point of view, because simply, if you have 1 million electron here, your target that all these 1 million electron transfer to reach the collector. If, for example, half of these electrons recombine in the base, then simply you lose half of your current. Then you will get lower current during operation. So the question now is how we can limit the effect of the recombination. Again, it's a limitation process because you can never reject, or you can never remove this impact totally. All the time you will have recombination. But what you are going to do is to design the BJT in order to limit the recombination effect. Okay, how we can do it? Actually, we have 2 approaches, or we have 2 procedures in order to limit the current or limit the recombination current. The first is here, this positive sign. If you remember, we described this positive sign before, which means a high doping region. So whenever I said that N plus B, that means that the doping here is much, much, much larger than the doping here. So for example, if you have here 10 power 18, you can have here 10 power 15, which means that this number is 10,000 greater than this number. So what is the impact of having a high doped emitter region? It's very simple. A high doped emitter region, that means that it includes a very large number of electrons. So if you have a recombination here, this recombination will affect a smaller amount. For example, if I told you that I have 1,000 electron here and I have 10 holes here, so this is 1,000 and this is 10. In case of the worst case scenario, when these 10,000 electrons pass over the base, 10, so we have this, we say that this is 10,000, I think, and this is 10. I forgot numbers, but okay, let's make it 10,000, 10. So this is 10,000 electron and this is 10 holes. So the worst case scenario is when these 10,000 electrons pass through the base, which includes 10 holes, 10 electrons only will going to be recombined because you only have 10 holes here. That's basically mean that simply means that you will only lose 10 electrons out of 10,000. So which is very, very limited loss. So by increasing the doping of the base of the emitter with respect to the base, you limit the effect of the base. So you limit the effect of recombination. Of course, you make another source of loss because whenever you decrease the doping here, that means that the overall current that can come from passing the holes from the base to the emitter, which is the whole current, will be also small. So you gain something that you decrease the recombination effect. However, you lose something that the base or the whole current coming from the base to the emitter will be limited. This is a simple trade-off. Usually in life we have trade-offs. Another approach or procedure in order to limit the recombination current is to have a limited or a very thin base, because simply the recombination effect is function in distance. Whenever the base is wide, then the probability is that during the electron journey in the base to be recombined, the probability will be high. Whenever this distance becomes thin or short, then this probability will be reduced, the probability of recombination. Accordingly, we always react to design our BJT with a very short or with a very thin base in order to limit the recombination. So these are the two approaches associated with reducing or limiting the recombination current, which is, of course, a bad or a disadvantage for a BJT. Okay. Finally, my dear students, I believe you already see this graph before, which is the IV curve for a BJT. During the previous slides, we have demonstrated together this very important and very interesting region of operation, which is the active mode. However, as I mentioned earlier, we still have another 3 modes of operation. What's called the saturation mode, what's called the cutoff mode, and what's called also the reverse saturation. As I mentioned, it's a matter of combination. So for the cutoff region, we have 2 junctions, both are reversed, so we don't have current. In the active region, which is the region we studied together, we have the first junction, which is the collector base junction, is reversing active mode. Yes, this okay. The emitter base junction is forward, and the collector base junction is reverse, which is the active mode. I think this is the one we studied together. Then we have the reverse active one, where we have the reverse. That's why we call it the reverse active, because we reverse the condition for active. So this emitter base junction turned to be reversed, and this collector base junction turned to be forward. This is maybe the most unused mode for BJT. It's not so famous at all. And this is the saturation mode where you have both in a forward bias. As you can see, the only difference between the active and the saturation is this collector-base junction. So if this collector-base junction is reversed, then we have an active. If this collector-base junction is forward, then you have a saturation. And the cutoff, of course, where both are reversed. During this course, we are going to make our main focus on the active mode because this is the most famous mode. However, we will discuss more about the other 2 or 3 modes whenever we are going to elaborate or we are going to discuss the EB model. So let's now start. What is the Ebers-Moll bipolar junction transistor model, or what we can easily abbreviated by the EM model? What is the EM model? This Ebers-Moll bipolar junction transistor model. It's very simple. It's actually somehow related or correlated to the way we discussed together our lecture today. Oh, the issue is very simple. If you remember, when we start to study this BJT, we consider it as 2 connected diodes. This is typically what we are going to do in the Ebers-Moll model. We will consider this as a 2 connected diode, as you can see. This is the base emitter diode, and this is the base collector diode. And we are going to express the current flowing in a diode, in a BJT, as the combination of 2 connected diodes together. But the main important issue is that these 2 diodes are not totally separated. They are overlapped or connected with this base terminal. That's why we have what we can call the mutual effect between these 2 diodes. Okay, so let's start to deal with these 2 diodes separately, as if each diode is a separated junction. So we have the base emitter junction, and this is simply the standard equation for the current flowing in a diode. This famous exponential equation. You have already seen it before in the PN junction lecture and maybe in your electronics 1 module. So this is a very simple one. And similarly here, of course, this is a forward bias whenever this junction is forward from the B to the N. Another equation or another model for the base collector junction. Again, this is the P type, this is the N type, this is the flow of the current, and this is the equation. So this is what we can call a separated model. But in reality, in the BJT, they are no longer separated. They are connected together. So this terminal is equal to this terminal. Accordingly, we have this overall schematic. Let's now start together to express each current flowing in this BJT or NBN junction. Okay, as you can see, we have 2 main gray arrows. This is the first one, which has 2 possibilities. The first is a current flowing from the base to the emitter. The second is a current flowing from the collector to the emitter. The third is a current, so this is the upper arrow. Let's go to the down arrow. In the down arrow, we have a current flowing from the base to the collector and a current flowing from the emitter to the collector. So these are the 4 possibilities we have in this schematic. Let's express together these 4 possibilities. So let's start with this configuration, and let's use this configuration to describe. Of course, we have some of these arrows which is very straightforward. For example, whenever you are in the active mode, we agree together that electrons will move from the collector to from the emitter, I'm sorry, to the collector through the base. This movement, because you have this is a forward bias and this is a reverse bias, so electrons will move in this direction. Accordingly, as you have a current flowing in this direction, then sorry, as you have an electron from this direction. So the current is usually defined as the reverse direction of an electron. So you have electrons going from the emitter. By the way, that's why we call the emitter is an emitter, because this is the region where you emit electrons, passing through the base, terminating to the collector. Accordingly, you should have a current flow from the collector to the emitter, which is this arrow. So this arrow representing the majority of the electron passing from, or the majority of the electron, yes, passing from the emitter to the collector, creating a current flowing from the collector to the emitter. So this is the first possibility. What about the second possibility? The second possibility is that although this is a p-type region, however, this region still have some minority electrons. These minority electrons were going to drift from the base to the collector, creating a current from the collector to the base, which is this current. So this current is conducted from the base, conducted from the base, conducted from the the base and going to the no, not this current. I mean this current. Conducted from the base and going to the collector. So this is another sort of current. Okay, so this is perfect. So we have current flowing from the emitter, from the collector to the emitter, due to the flowing of electrons from the emitter to the collector. And we have current flowing from the collector to the base due to the electron movement. Let's see again. Okay. Let's turn to the holes. What about the holes? As you can see here, we have a hole flow from the collector to the base. So we have another current here. But the majority of the current will flow from the hole, from the base to the emitter. This is another majority current, as you can see here, from the base to the emitter, which is this one, from the base, the emitter. So this is another source of a majority current. So this arrow represents two majority currents. The first majority current is due to electrons, which create a current from the emitter to the base. And the second majority current is due to holes. Whenever holes are conducted from the base to the emitter, creating a current flowing from the base to the emitter. So this is the resultant of the first model, where you have a base current and a collector current flowing to the emitter. On the other hand, whenever we are talking about current flowing to the collector, this current is due to the minority carriers. When we have electrons, when we have holes going from the emitter to the collector, or going from the base to the collector, which is the reverse direction of a current. So in the active mode, your current will be this one, which is a majority current due to either holes coming from the base or electrons coming from the emitter. When you have a minority current, then this will be in the bottom arrow, which is a current going to the collector, which is outside the active mode equation. Accordingly, we can write these two equations, which is, of course, you are not requested to memorize. However, this is the combination of these two currents, the majority carrier current and the minority carrier current. And these are the two models. It's simply a resultant of merging these two models together to form this general model for the majority carrier currents and the minority carrier currents. Okay, so As you can see, this is simply a diode equation here and a diode equation there. However, but we have a different definition for the saturation current in the diode equation. Okay, let's do more about this model, what we call the EM model or the Ebers-Moll model. So let's continue in this direction. So we can simplify this EM or Ebers-Moll model into a very simple schematic, circuit schematic. As we see, we have two p-n junctions. And for each p-n junction, you have two conditions. Either it's on a forward or it's a reverse. This is the briefing. So this is the base emitter junction. If this is a forward bias, then the current will be conducted in this direction. If it's a reverse bias, then the current will be conducted in this direction. Similarly here, for a base collector model, if it's a forward, the current will be conducted in this direction. If it's a reverse, the current will be conducted in this direction. So for example, if I ask you, please show me the path of the current whenever the transistor is in an active mode. So as you know, in an active mode, you have the base emitter junction reverse, the base emitter junction is forward and the base collector junction is reverse. So the current will take this path. This is a reverse junction and this is a forward junction. So this is the path of the current. That's why we have a current. Okay, what about the, for example, the cutoff mode? In the cutoff mode, both are reverse. That's why no current path, because this current will be cancelled by this current and the overall current is zero. So you can track the path of the current for any mode out of these four modes using this simplified Ebers-Moll bipolar junction transistor model. Okay, what is next? In the next stage, my dear students, we are going to plot the electrons and the holes carrier concentration with respect to the NPN model. Herein, we have to recall the example when we do this test, if you remember, for the p-n junction. In the p-n junction, we have plotted together the electron and hole carrier concentration. And now we are going to do the same procedure whenever we are studying a BJT or a bipolar junction transistor. So, perfect. So let's start with recalling the knowledge we have gained from the p-n junction. So, in a p-n junction, let's start with the thermodynamic equilibrium case. Whenever you have, this one is not working. Yeah, that's working. That's perfect. So whenever you have a Fermi level, this is an EF, which is a horizontal line because this is under thermodynamic equilibrium. And then we start to plot your p-n junction. Oh, no way. So we are going to start to plot the p-n junction in this way. So this is the N region, and this is the P region. Okay. If you remember, my dear students, whenever we start to plot this energy band diagram, we also plot what's called the carrier concentration. So here is the same axis. And here we are plotting N and P, the number of electrons and number of holes. If you remember, it was very straightforward. I told you that in this region, electrons, let me use another one, maybe it works. Okay, yeah, good. So herein, electrons are majority. So we have a huge N, on a correct one. So this is the majority, which is ND, because in this region, N are majority carriers. And in this region, N are minority carriers. So here we have a minority, which is, if you remember, N small, sorry. So it's Ni squared over Na. And we connect them together in this manner. Similarly, in the P type, or in the holes, here holes are majority, which is Na, and here holes are minority, and then we connect them together in this. So this is the holes and the electron variation in a p-n junction. Now, what if, for example, we apply a positive voltage, or we apply a forward bias to this junction? So we connect this junction in a forward bias. Let's see what will happen. So if you connect this junction in a forward bias, that means that this barrier will be reduced in this manner. So now this barrier will become V node minus Vf, if you remember. So now this is a forward voltage, but this voltage is still below than the building potential. Let's now try to reflect this on the graph. What will happen? Whenever the barrier reduced, then some electrons will go to transfer from the N region to the P region. And some holes were going to be transferred from the P region to the N region, because you have a lower barrier. So some electrons can escape and go to the other side. If you remember, my dear students, in this case, I told you the example of a rich man and a poor man, if you remember this example. This is the one who has a huge amount of electrons. This is a rich man with respect to the electrons. So he has, for example, $1 million in his bank account. And this poor man has only $10. So what if this rich man, which has $1 million, donates $1,000 to the poor man? The bank account for the rich man will be reduced by 1,000. So it becomes 1 million minus 1,000, which is nothing. However, the bank account of the poor man will be enhanced, will be increased by $1,000, which is a very big number with respect to his starting bank account, which is $10. So it becomes $1,010. So whenever we have a carrier transport, majority carriers are much affected with respect to the, sorry, minority carriers are much affected with respect to the majority carriers. That's why, if you remember, when we replot this graph after the forward bias, I plotted like something like this. Nothing have been changed in the majority. However, the poor man, the minority, have been increased due to the flow of the electron. Why I'm recalling this story? I'm just recalling this story to make sure that you understand that whenever we study the carrier transport, we are mainly interested in studying the minority carriers, not the majority carriers, because usually majority carriers are not affected. Minority carriers are affected. Majority will not be affected, or are not going to be affected. That's why now in the PNP or the NPN junction transistors, we are going to study only the minority carrier, not the majority carrier. Let's do it. Okay. So what we have is a NP and graph. First, we can plot everything under thermodynamic equilibrium. So under thermodynamic equilibrium, life is easy. We have a formula. This is a formula. And we can plot everything with respect to this formula. So as you can see, this is NPN junction. As usual, you know my plotting or my sketching is not so good. So this is an NPN. Okay. Now, if I told you, please sketch the minority carrier concentration in these three regions, it will be very easy task. So we have three sets of minority carrier concentration. This is an N region. So simply the minority carriers will be due to hole. So we have holes here, which let's call it, for example, PE. What I mean by PE is the holes in the emitter region. And let's do it node to say that this is under thermodynamic equilibrium. So this is hole. And we have also some electrons here. So for example, let's do it here. Let's call it NP node. So this is electrons in the base at thermodynamic equilibrium. And finally, we have some, again, holes here, which is P, C node. This is holes in the collector region at thermodynamic equilibrium. Of course, the levels here can vary depending on the doping level. So if you have a high doping, then the minority will be reduced. If you have a low doping, then the minority will be increased. So this is inversely proportional due to the mass action law, because simply minority carriers is Ni squared over N, which is the doping. So whenever N increase, the minority carrier decrease and vice versa. So you can adjust these levels based on the condition you are plotting with the doping in the emitter, the base, and the collector. So this is the emitter, this is the base, and this is the collector. Okay, that's nice. Now, what we are going to do is that we are going to demonstrate these graphs far from thermodynamic equilibrium. I mean, whenever you have some biasing condition, we are going to represent the most three used modes for a BJT, which is the active mode, the cutoff mode, and the saturation. Let's start with the most famous one, which is the active mode. And let's see how this active mode shall affect the minority carrier concentration in a BJT. Let's see. So now we have our PN junction. So this is N, P, N. We need to make it in an active mode. So active mode means that this junction is connected in a forward bias. That's why I'm connecting the base to a positive and the emitter to a negative. So don't forget that this is this emitter, this is the base, and this is the collector. And this should be in a reverse bias. That's why I'm going to connect this in a positive and this in a. So this configuration reflects an active mode configuration. So the effect of this active mode the configuration on the energy bandwidth, we already have studied that whenever this is a forward bias, then you should expect something like that. And then you should expect something like that. So this is a forward bias and this is a reverse bias. I think we already see this graph before, more better than what I'm doing here. just to elaborate the story. Okay. Now let's reflect this on the electrons in the holes. How the minority carriers will be affected by this diagram or by this binding condition. What will happen? So that's it. Now, once you make this junction forward, what is going to be happen? Very simple. Here you have a majority of electrons. This majority of electrons will going to drift to this p time. That simply means that this electrons here, which is majority, sorry, with the minority, will be increased due to the drifting of electrons from the inside on the left-hand side. So you should expect that this go up somehow. And similarly here, holes will drift from the base to the emitter. That means that the minority holes in the emitter, which is this one, will going to increase somehow. So here you should see something like that. Because now this increase, we call it usually delta P. This delta P increase is due to the flowing of holes from the base to the emitter. And also you should see something increasing here. Okay, then what will happen on the other side? Now this is a reverse bias. What do you mean by reverse bias? Reverse bias, that means that holes will not, holes which is the majority carrier will not be affected. What will happen due to this majority, due to this reverse bias? That minority electrons here will going to drift. So electrons were going to decrease. And minority holes here will going to drift. So you will find something like that. Holes now this delta P is in negative, not in positive, as you can see. Here delta P is positive because you have this junction is a forward bias. That's why the current increase the minority carrier. However, here this is in a reverse. So minority carrier will be reduced. If you remember, the poor man will give money to the rich man. So that's why holes now will be negatively affected and the electrons will be negatively affected. So this is the case for an active region. Let's see it in a better manner in the presentation slide. So this is the case, my dear students. Here, both minority carriers are added because this junction is forward. So the current is going to increase the minority carrier. So the electrons increase in the base, the holes increase in the emitter. But this junction is a reverse junction. So a reduced minority carriers is observed here and there. So this is the graph representing the variation in the minority carrier due to an active junction. Now, I believe you can pick the idea. So whenever you have a forward bias, minority carriers will be added, will be increased. Whenever you have a reverse bias, minority carrier will be reduced. So if I told you, please plot a similar graph for the cutoff region, for example. So you will expect something like that. Minority carriers in both regions or in the three regions will be reduced. As you can see, a reduction here, a reduction in the base, and a reduction here, because simply both junctions are reverse bias junctions. So minority carriers increase. Please don't forget, the minority carrier is the reverse bias means that the poor man pay money to the rich man. So the poor man even lose the little amount of money he has, which is the case. However, the forward bias means that the rich man pays money for the poor man. So the bank account for the poor man is enhanced, is increased. So now we have to reverse bias junction. That's why the minority carrier is negatively affected. Let's do the third one, which is the saturation. Both are forward. So all minority carriers increases, as you can see here. Here increase, and here increase. Of course, I'm saying that increase with respect to the thermodynamic equilibrium case, which is the dotted one. So as you can see, everything increases here because both junctions are forward biased. So this is simply how you can use the EM model in order to demonstrate the minority carrier variation in NPN junction. Again, we are interested in minority carriers because these carriers are those carriers which are affected. Majority carriers, rich bands has no effect due to biasing conditions. They always has a very large amount of money. So whenever you take from them, their bank account will not be affected. This is simply the majority carrier. But minority carriers are those carriers which are strongly affected by any small variation or any type of carrier transfer. Okay, so this is a termination for chapter number 5, the bipolar junction transistor. We have studied together the carrier transport model through the energy band diagram, the different operation conditions, the EM or the Ebers-Moll model in a form of a two connected diodes, and how we can express different type of current using this EM model. Then we finalize the chapter by studying the variation in the minority carrier under 3 different carrier conditions. This is all we have. The next chapter, which will be the final chapter, it's some sort of showing up chapter where we are going to discuss together the most recent technology in the field effect transistor. We are going to discuss a collection of technologies, starting with the tunneling field effect transistor, thin film field effect transistors, and OFET or organic field effect transistor. It's something to be close to the most recent technology in the FITs or in the field effect transistor. Thank you very much for your concentration, and see you in the next chapter, chapter number 6, which will be the terminating chapter for this module. Thank you, and see you next week.